So let's start with a CMOS inverter example. So what is an inverter? It is a NOT gate, right? We have already seen how to call the NOT gate in Verilog, either by using primitives like NOT, out, comma, in. This will give you NOT gate operation, or you can directly write out is equals to NOT of in. This is an operator which will do the inverter operation. Okay. So now in this example, I want to design a CMOS inverter or CMOS NOT gate using switch level modeling. So first of all, we have to see the schematic of the NOT gate. The schematic of NOT gate using PMOS and NMOS is, this is VDD and this is a PMOS and this is an NMOS, right? PMOS, NMOS. You connect these two gate terminals and apply the input here, you will get the output here, right? This is the schematic of the inverter or NOT gate. So we want to write the switch level modeling for this inverter or NOT gate. The VDD here will be a power and the ground here will be a GND net. So how to define this PMOS? We have already seen. You just need to write PMOS and then you can write the name or not, it is your wish. Right now I am defining the names P1 and N1. So P1, here the data is PWR and output is this out, comma, what is the other terminal? We have to give P control. The P control here is in, right? So let's define this module. First of all, we have to write module and name of the module. I am giving a name of my inverter. Okay, inside this module, I have port declaration. We have one output port and then one input port, right? So this is the port declarations. Now I will define the ports: output, out, input, in. Okay. Now we need to define these supply and grounds. So the syntax is supply 1 will be power, supply 0 will be GND. After this, we have to call this PMOS and NMOS primitives that are available in Verilog. So I am calling PMOS, the data is PWR, output is out, and P control is in. The name I am giving is P1. Similarly, I am calling NMOS, N1. Here the data is out and the out is ground and the N control is in, right? And module. So this is your inverter using switch level modeling. You can call this inverter in any other module, like in top module or in stimuli module. You can call this directly like this, my inverter, and give a name, mi, any name, and then you can call with your local variables, out p comma in p, like this. So this will call the inverter module and you can apply the different stimuli to check the performance of this inverter. So this is how you can design the inverter using switch level modeling. Now let's see some complex gates like NOR gate or NAND gate. These two are universal gates, right? Once you can able to build these two universal gates, you can build any digital logic circuit. So let's focus on building this universal gate. First of all, I will draw the schematic of NAND and NOR gate. So how does a NAND gate will look like? What is the operation of NAND gate? NAND y is equals to a dot b whole bar, right? So I'm taking this as VDD line, which is a power line. In NAND gate, the PMOS are connected parallelly and NMOS are connected serially. I am not explaining how this circuit is drawn, but this is the circuit of the NAND gate. Similarly, the circuit of NOR gate will be PMOSes will be connected serially and NMOS will be connected parallelly. Right? This will be my ground. This is an NMOS. Let's call this N2, N1, P1, P2. So this is the output. This is in 1, in 2. We have two inputs. So in 1 and in 2. Similarly, this will be in 1 and in 2. In 1, in 2, in 1, in 2. This will be my output. P1, P2, N1, N2. Okay, these are the schematics of NAND and NOR gates. Power, ground. So let's write the module definition for, let's say I will write the module definition for NOR gate. The NAND gate will also be similar. You can write by yourself. So I am writing the NOR gate module. So we'll start with module. Name of module is my NOR, and I have one output and two inputs in 1, in 2. I am defining output is my output node, input, two inputs in 1 and in 2. Okay, I'll require one wire, so I'll call this wire as, let's say, wire W. Okay, this is a wire, so I'm calling a wire W. Now I need to call the primitives of PMOS and NMOS to properly connect the nets. Right, nets are wires. So first PMOS is P1, PMOS, P1. Before this, I need to call the supply and ground also, right? So I need to write supply and ground lines, which is supply 1 is my power and supply 0 is my ground. Now I'll call the primitives PMOS, P1. It is connected from power to wire W and control voltage is in 1. Similarly, PMOS, P2, it is connected between W and out, and the control input is in 2. My NMOS, N1, is connected between out and ground, and the control input is in 1. Similarly, NMOS, N2, is connected between out and ground, and the control input is in 2. Now these four MOSFETs are connected as intended. Let's end the module. So this is your NOR gate. Similarly, you can write the NAND gate also. For NAND gate, what will be the connections? The PMOS, drawing very badly. Let's draw it one more time. The PMOS are in parallel for NAND gate, and NMOS are in series, right? So I am writing the definitions of PMOS and NMOS here. PMOS, let's say P3, P4, N3, N4. My P3 is connected between power and output with a control input of in 1. Let's say this side is in 1 and this side is in 2. And my PMOS P4 is connected between, again, power and output with control input of in 2. Similarly, my NMOS N3 is connected between this output, and let's write a wire W, and the control input is in 1. My NMOS N4 is connected between wire and ground with control input of in 2. So this is how you can define the NAND gate. Okay. Now let's see some complex circuit like multiplexer using PMOS, NMOS, or directly we can use a CMOS, right? We have already seen we can use the CMOS circuit like this, which is having both NMOS and PMOSs and one output and one input, P control and N control. So first of all, we'll draw the schematic of the 2:1 multiplexer using this CMOS gate. So how does the 2:1 multiplexer will look like? It has, what is the purpose of 2:1 multiplexer? It has two inputs, and based on the select line, one of the input will be connected to the output. This is in 1 and in 2. Based on the select line, if the select line is 0, then in 1 will be connected. If the select line is 1, then in 2 will be connected to the output. So the same kind of operation can be obtained with this schematic. Let's say in one path, I have one CMOS gate like this. This is P control, this is N control. And in other path, I have one more CMOS gate like this. So what ultimately I want is, if this path is turned on, this path should be turned off, right? So how can I do that? I will control such a way that if this signal is on, then this path will be off, right? So I am giving this as my control input from outside. If this is 1, then if it is connected to 0, then this is also on. So we don't want that, right? What we want? We want this to be, if this is 1 and this is 1 means here 1 is appearing, so this PMOS will be turned off, right? So this kind of operation we want. So what I am doing here is, understand this carefully. If this signal is 1, then this NMOS will be turned on and this PMOS will be turned off. So the signal will flow from here to here. Let's say this is my input. It is connected to both of the terminals. No, this will be my input, right? So it is connected to two different inputs, I0, I in 1 and in 2. And this will be connected to my output. This is my output. So the output will get signal from in 1 in this case. If this signal is 1, then it is coming through this. But you need to give negative logic also for PMOS. So that is why I will keep a inverter here. Let's keep an inverter here to give the negative logic also, right? So what does I mean? If I provide a signal of control signal S is equals to 1, so the 1 will appear here. So this NMOS will be turned on. If it is 1 here, the inverter will convert 1 to 0. So this will be 0. So this complete CMOS circuit will be turned on. Now it has two paths. It will flow like this as well as it will flow like this, right? The input signal is completely given to output through this CMOS switch. Okay. Similarly, if this is 0, then this PMOS will be turned on and this NMOS will be turned off. If it is 0, this will be given as 1 to the P control. So this PMOS will be turned off. So enter this path will be turned off. It has path flowing like this. We want path from this also. So we'll take this inverted input. I'm taking this inverted input and connecting it to this NMOS gate, right? So this is the complete circuit of 2:1 multiplexer. Let me draw it one more time. So let's draw this clearly. So we have two CMOS switches and we have two inputs, in 1 and in 2. If my S is equals to 0, then if it is 0, then my in 1 should be connected. So I am changing the positions of in 1 and in 2. If my S is equals to 0, I want my in 1 to pass, right? So if my S is equals to 0, then 0 will appear here and this PMOS will be turned on. Since it is inverted and given it to NMOS, so the in 1 will flow from this and this, both the PMOS and NMOS switches, towards output. So output will be in 1 if my S is equals to 0. Similarly, if my S is equals to 1, then 1 will come here. Since 1 is the control input for NMOS, so this NMOS will be turned on. The 1 is converted to 0. Since control input for PMOS is 0, so this PMOS will also be turned on. So the in2 will pass to output if S is equals to 1, right? So this is the basic schematic of the 2:1 multiplexer. So let's write the module definition for this. We'll start with module my MUX. What are the outputs? We have one output and two inputs, in 1, in 2, and one control input S. Okay. Now define the ports: output out and input in 1, in 2, S. Okay. Let's check, do we need any wires? Yeah, we need a wire here to get the inverted output. So let's define a wire S bar, which will give you the inverted output. So either you can use a inverter or you can use a NAND or NOR gate as an inverter, right? We have already seen how to get the inverted operation from NAND or NOR gates. So this is a NAND based inverter and this is a NOR based inverter. If you connect two inputs together, then this will be acting as a inverter, right? Either you can use direct inverter or you can use NAND or NOR gates as an inverters also. So first of all, I have to convert my S to S bar, right? So I am using an inverter. I can either use the Verilog primitive inverter or I can use my own inverter that I have defined in the previous slide. So my inverter Mi, my output will be S bar and my output is S. Now the inverter is done. So this line is S bar and this line is S, right? So now we'll write the definition of this CMOSes. Let's say this is C1 and this C2. So CMOS C1, my output is out, my input is into, and my N control is coming from S, and my P control is coming from S bar. Similarly, my CMOS C2 will be having out, in 1, and my N control is coming from S bar, and my P control is coming from S. That's it. Now your complete definition of 2:1 multiplexer is done and module. So this is how you can define a 2:1 multiplexer in switch level modeling. You can call this model wherever you require. You can use the 2:1 multiplexer to build 4:1 multiplexer or any complex circuits you want. Now let's see a sequential circuit of latch. How to what is the main application of latch? To store a 1-bit data like this. If you into a back-to-back inverter pair. So what is the operation of latch? If you store any data inside this, let's say 1 is stored here, the 1 will be inverter to 0 and the 0 will be again inverter to 1. So the back-to-back inverters will hold the data, whatever the data you have written into it. If you have written 1 here, then it will hold the 1 until the VDD is present, power and ground are present. So in the previous slide, I forget to add power and ground, right? Do we really require power and ground here? Do we have power and ground terminals here? No, right? That's why I haven't added any power and ground. So in this case, unless and until you drop the power or ground, this latch will hold its own data. So let's first draw the schematic of the latch, then we'll try to write a module for it. So the latch schematic will look like this. So the purpose of latch is to hold the 1-bit data, right? So to hold it, we will require a 2 back-to-back inverters. This is called back-to-back inverter pair. Okay. This is my Q bar. First, let's draw the symbol of it. This is a latch which is having Q bar and Q as outputs and D as my input, and we'll have clock. Okay. So Q bar, this will be my Q, and I have one CMOS gate. This is a CMOS gate. Okay. Will look like this. This I am calling it with name C. So this is a CMOS gate, and then the control will be negative logic. That's why I was putting bubble here, and then we'll have one more CMOS gate C1, and the control here is positive logic. That's why there is no bubble. So this is data and this is clock. So if you can see the operation of this latch like this. If the clock is 1, so what happens? This CMOS gate will be turned on because the control logic is positive here. So the data will be latched to here. The D will appear here. But since clock is 1, this CMOS gate is off. So this back-to-back inverter pair is off. Only the data is latched here. We have written the data, but we haven't holding the data. We haven't holding or we haven't sent the data towards Q. Okay. Once the clock is equals to 0, then this CMOS will be turned off and this CMOS will be turned on. So it will loop the data whatever you have written earlier. The D will be, since this CMOS is turned on, so this will be act as a connector line like this. So it will loop the data that you have written. That data you can get from Q bar and Q as well. So whenever the clock is equals to 0, the output will be available. Whenever clock is equals to 1, the output is the input is written into the latch. So this is the operation of the latch. So now let's write the module for this. So let's start writing CMOS module my latch. So what are the outputs for this? Q bar and Q, and what are the inputs? D, comma, clock. Okay, let's delete this. So we'll require two CMOS gates and two inverters, right? These are the primitives that we required. Two CMOS gates and two inverters to create a latch. Okay. Now I am declaring the ports: output Q bar, comma Q, input D and clock. Okay. Do we require any internal wires? So this is my D. So we'll require a wire here. Let's call it as wire E, and any other wires. This is already connected to Q, so we don't need a wire here. This is already connected to Q bar, so we don't need a wire here. Only one internal wire we require. So we'll write wire E, and then we'll require a negative clock as well, right? So this is this we want as a negative clock. So let's declare a wire of clock bar, clock B. Okay, that is the negative clock or complement of the clock. So first of all, create the clock B by using my NOT gate or my inverter. What is the definition I have given? My inverter, right? My underscore inverter. I'm using my underscore inverter mi. In this, my output will be clock B and my input will be clock. Okay. Now I will write the definitions of these inverters and CMOSs. First, we'll write CMOS C1. CMOS C1 is connected between output E and input is D, and its P control and control is clock, and its P control will be clock bar. Similarly, my CMOS C2 is connected between my output as Q and my input as E, and its clock is clock bar, and control is clock bar here, and P control will be clock. Okay. Now we need to write definitions of these inverters. I will call my inverter mi. This is mi2 and this is mi3. I'm calling with these names. So mi2, what is the output? Output is Q bar and its input is E. Similarly, my inverter mi3, its output is Q and input is Q bar, right? And module. So this is the definition of your CMOS latch in switch level modeling, right? This C2 should have Q as output or E as output. It can be Q or E, but usually we'll prefer E as output and Q as input, right? Because this is the driving node for this CMOS inverter, not this. Because the data is latched like this, so Q will be the driving node and E will be the output node for this C2. Okay. Similarly, for this C1, D will be the driving node. The data is given from this side and output is appearing at E. That's why E is the output and D is the input. For C2, Q is the driving node and E is the output node, not in the reverse order. So you have to remember this. So this will be your definition of C2 and this will be your definition of C1. So this is how you can build any circuit using switch level modeling. As you can see, the same operation can be performed using data flow or behavioral modeling very simply, but to define this operation in switch level modeling, we will require different primitives like NOT gate, CMOS inverter, all these things. So it will become very complex if you try to write complex circuits using switch level modeling. That's why designers will move to either high level language like data flow modeling or behavior modeling compared to the low level language like gate level or switch level modeling. So this is all about switch level modeling. Now let's see a concept called timing and delay. We have been seeing these timings and delays from the beginning of this course. So let's broadly classify them. If we broadly classify them, there are three types of delay models that are available. First one is distributed, and second one is lumped, and third one is pin to pin delay, or we can call it as path delay also. So what is this? A distributed delay is, let's say you have a circuit like this, two AND gates connected to one more AND gate. So let's name A, B, C, D, and this wire is E and F. This is output. So in case of distributed delay, each gate will have its own delay like this. So the delay is distributed among all the gates. So this is distributed delay. The same thing if we draw, and instead of giving distributed delay, you can give A, B, C, D, E, F out. You can give lumped delay. All the delay, whatever you want, you can merge it into a single delay. Let's call this as a hash 13. So here we are not distributing the delay, we are directly lumping it into a single gate. That will give you the total amount of delay from this to this. This is distributed and this is lumped. And the third case is pin to pin delay. So the name itself is suggesting you can have delay from one pin to other pin like this. If you want to have a delay from A to out with a 9 nanosecond delay, then you can define pin to pin delay using spec. SPEC. I will explain what is this in the next slide. But these are the different types of delay models we have: distributed, lumped, and pin to pin, or this is called path delay because it is showing the path of the signal, right? So these are the three different models of delays we have. Now let's model the path delay using specify block, right? So first of all, we'll see the distributed and lumped delays, then we'll move to path delays. So first let's see the distributed delay, the same circuit I'm taking. Let's say I have delay of 5 nanoseconds for this AND gate, and let's say 6 for this AND gate and 7 for. We can have different delays for different AND gates as well. So A, B, C, D and out. So why do we have different delays for different AND gates? Imagine like this. As a circuit engineer, what is your goal? Your goal is to optimize the design, right? Optimization in the sense, first thing is your speed should be as high as possible, and second thing is the output signal should drive the output from one circuit should drive the input to the other circuit. So you need to take consideration of two things: one is speed and second thing is driving strength. So usually the circuit engineers will concentrate on both the things, but these two are inversely proportional to each other. If you want high driving strength, your speed of circuit will be reduced. If you want high speed, then your driving strength will be reduced. That's why in this case, the speed of this AND gate is reduced. That is, the delay is high, but its driving strength is high. Similarly, here we compromise the driving strength, but we increase the speed by decreasing the delay. So that's why different AND gates might have different delays also. As a circuit engineer, you need to know why we will have different speeds and different strengths, right? You can design accordingly to your application. Whether if you require high strength, then decrease the speed. Whether if you require high speed, then decrease the strength. Okay. Now let's define the delays for this module. You can either define using either gate level modeling or data flow modeling, right? How to do that? We have already seen this many times. We'll just call the AND gate here, and let's say A1 is my AND gate. Its output is E, input is A comma B. Now I am defining a delay of hash 5. Similarly, my AND hash 6 A2 output is F. This is F, and inputs are C comma D. So this is how you can define delays in gate level modeling, or you can use data flow modeling like this. If you want delay of 5 nanoseconds between E is equals to A and B, and delay of 6 nanosecond F is equals to C and D. So this is distributed delay model. So if you want a lump delay model, what you can do, you can simply define E and F without any delays, and you define a delay at output node. Output node have, let's say, how much delay I want, let's say 13 nanosecond, then hash 13 out is equals to E and F. So we have only lumped the delay into one single gate. So this is lumped model. So this is how you can define both distributed and lumped using gate level and data flow modeling. Now let's see how to define the path delays or pin to pin delays using specify block. For this we will require a keyword called specify and end specify. Remember, these two should not be inside any initial or always block. These two should be separated from them. So how to define this? Let's say I am taking the same circuit and I want to have a pin to pin delay from my A to, this is the path A to E and E to out. I want a delay of, let's say, 9 nanoseconds. Okay. Similarly, from B to E, I want to have 9 nanoseconds. And C to F, I will have 11, and D to F, I will have 11 nanoseconds. So how to define this? We will use specify block like this. Specify, this is the keyword you need to use. Inside the specify block, you can write your delays from A. So this is the symbol you need to use, is equals to and greater than. What is the symbol for non-blocking? Less than and equals to. Okay. Don't confuse that here. So you can see the symbol itself is representing like this. It is going like this, right? So from A to what node I want? Output. How much delay I want? From A to output, I want a delay of 9 nanoseconds. Similarly, I can write from B to out, I want a delay of 9 nanoseconds. From C to out, I want a delay of 11. From D to out, I want a delay of 11. Specify and end specify. This is how you can define the path delays. Once the path delays are defined, you can directly write either using gate level modeling or data flow modeling as it is A comma B and F is equals to C comma D and out E comma F. So here I am not specifying any delays, but since I have specified the delays here, it will consider the delays. So this is how you can specify the path delays. Okay. Now let's see some additional features in the path delays. If you want to map the array, let's say you have an array of 31 down to 0. So you don't need to write every time a of 0 to out how much delay I want, a of 1 to out how much delay you want. You don't need to write every time like this. You can directly use a symbol called asterisk is equals to. Okay. What does this do? Asterisk greater than, sorry. Asterisk greater than, what does this do? It means connect all the nets inside that vector to the particular pin. Okay. So how to define that? Let me write the schema syntax. So if I want to connect every bit of A, let's say A is a 32-bit data like this. A is 32-bit data, and if I want to connect every bit of A to my output with some delay, then I can use specify A asterisk greater than, what is the output node? Out is equals to 9. So what does this mean? It will connect every bit A0, A1, A2, A3 up to A31. From A to output, you have A and you have output. It can be any combination circuit between them, but it will connect the A pin to output pin, all the pins inside this A to output pin with this much delay. Specify, and we should end the specify. Okay, this is the syntax for that. You can even parameterize this delay. Right now I'm giving the numbers, right? You can even parameterize them by using spec param. So usually we'll use the keyword called parameter to define the parameters, right? Here to specify the parameters, we need to use a keyword called spec param. So let me write that. So I can use the statement of spec param. So this is used to generalize the delays you want. So I'm generalizing the delay from D to Q. Let's say there is a flip flop and I have D. So this is my D and this is my Q and I have clock, right? So I can specify the delay from how much delay I want from D to Q and how much delay I want from clock to Q. These are very, very important parameters when you design a flip-flop, you need to know how much delay it is taking to carry the data to Q and how much delay it will take once you turn on the clock, how much delay after delay you are getting the Q data, stable Q data. So we can define like this: spec param D2Q is equals to 9 nanoseconds and spec param my C2Q is equals to, let's say, 11 nanoseconds. So you can define like this, and after this you can use these spec params in your specify block. Specify what you want. You want delay from D to Q, right? So I need to write D and then to Q. How much delay? Either I can write 9 directly, or I am generalizing this with this parameter name. So I am writing D to Q. So later if you change 9 to some 90 or 19 or any number 21, then this D2Q will automatically update that number. So that is the advantage of this generalization using spec param. So similarly I will write C2Q in my C2Q. Okay, this is my clock, since I have given clock as my name. So and specify. So this is how you can use the spec parameter to generalize the delays. Okay, we'll see one more additional feature, like you can give conditional path delays also. So what does this mean? Whenever the condition is satisfied, then only give that path delay. So how to write that? You can write like this: if let's say my B is the signal, and if my B is 1, this is the control signal I want. If my B is equals to 1, then let's have a delay of A2 output as 9 nanoseconds. Or if my B is 0, then let's have A2 output as 11 nanoseconds. So this is how you can specify condition as well and path delay. This should be inside the specify block, right? Whenever you are writing this is equals to greater than delays, you have to specify inside the specify block. Specify and specify. Okay, this is how you can give the conditional path delays. Apart from this, you can even give rise delays, fall delays, turn off delays that we have been seeing, right? Here I'm only giving the single number like 9 or 11. You can even specify what is the rise delay, what is the fall delay, and what is the turn off delay also by giving multiple numbers like this. Let's say I'm taking C2Q as my 11 nanoseconds, right? If you want rise delay and fall delay should be different, then you can specify like this: spec param, I'm generalizing them. My T rise is equals to 9 nanoseconds, let's say, and my T fall is equals to 11 nanoseconds. So I'm defining the parameters T rise and T fall, and then I will use these parameters like this. My clock to Q, I'm having a delay from clock to Q. Here, instead of writing a single number C to Q, I can either write C to Q or 11. I'm writing here T rise and T fall. So what does this do? It will have a rise delay of 9 nanosecond and fall delay of 11 nanoseconds, right? If you specify T turn off also, you can specify T turn off and give that here T fall comma T turn off. Okay, this is how you can give different rise time and fall times to your path. Okay, you can even specify transitions also. How much delay you want from 0 to 1. If the signal is flowing from 0 to 1, how much delay you want? Or if it is going from 1 to 0, how much delay you want? Or it is going from 1 to Z, how much delay you want? You can even specify them. There is a particular order you need to follow to specify them. Let me write that order. So first of all, we have to define them using spec param, right? Spec param, use this SPEC param to define those delays. So in SPC param, I am defining my T0 to 1 is 9 nanoseconds, let's say, or my T1 to 0 is 11 nanoseconds, or T0 to Z is how much? 5 nanoseconds. Similarly, you can write T Z to 1, how much? 5 nanoseconds. T 1 to Z, let's say 6 nanoseconds. T Z to 0, 8 nanoseconds. This should be comma, right? Because I'm using single spectrum. So this is first you will define these terms, and then how to assign them. You need to follow the order. The order should be like this: 0 to 1 and 1 to 0. Later 0 to Z, Z to 1, 1 to Z, Z to 0, and 0 to X, X to 1, 1 to X, X to 0, X to Z, and Z to X. Whatever the values you specify, it will take in this particular order only. So even though if you give the name of T01 and if you specify it here somewhere in the third variable, it will consider it as a 0 to Z delay only. It will not consider it as a 0 to 1 delay. So order is important. In this order only, we will specify the delays we want, like this. Let's say I want to have a clock to Q delay of different parameters. T01, I can name anything here. I can name time 01 or uh, T delay 01, any name, but it should be in this order. First parameter should be 01. Similarly, let's say I named it as D10. Any name I can give, but the second value, whatever you have given inside this bracket, it will be considered as 10 delay. Similarly, the third value, whatever you gave here, let's say X0G, whatever the name it is, but the third value will be considered as 0 to Z delay. In the same order, it will consider TZ1, T1Z, any name, but the order will be this. Okay. So by this way, you can even specify 1 to 0, 0 to 1, or 0 to X and 0 to Z delays as well. Okay. If you don't specify anything, then it will take it as a 0 delays. Let's say you have only specified 2 delays, T0 to 1 and T1 to 0, and close the bracket, then all the remaining will be taken as 0 delays. Okay. So that is how you can specify different delays using this spec param and specify blocks. So this is all about timing and delay. Now let's move to one advanced concept called user defined primitives. What are these user defined primitives? In Verilog, we have primitives like NOT gate, AND gate, NAND gate, NOR gate. These are all the Verilog primitives that are already available. Let's say you want to define your own primitive. So how to do that? You can do that by using a table, truth table. What are the truth table you want to define? You define that inside the table, and then you can write your own primitives. There are two types of primitives you can define, either combinational primitive or sequential primitive. We'll see them one by one. So what are the parts of the UDP definition? Whenever you are the UDP means user defined primitive. Whenever you are defining a UDP, the UDP first you will have a name and terminal list. Just like module, the UDP will have its own name and its terminal list, and then we will declare the terminals. Just like in the module, we have declared the outputs and inputs. Here also we will declare the terminals, and we will have UDP initialization. If there is any bit to be initialized, only in the case of sequential it will be helpful. You need to initialize that bit, and we will have UDP state table or truth table, you can say, and end of the UDP. So these are the parts of the UDP primitives. We will see one by one when we write our own UDP. So before writing the UDP, we have to take care of these rules. So the rules you need to follow is the UDP can take only scalar inputs. What does I mean? The UDP should not have a vector inputs like this, 31 down to 0, or any vector inputs, or 3 down to 0. Any vector inputs it should not have. It should have only scalar inputs. But you can have multiple inputs like A, B, C, D, any number of inputs. But all these inputs should be scalars, but not vectors. Okay, this is the first rule, and the second rule is can take only one scalar output, and multiple outputs are not allowed. Okay, the output should be only one output, and it should be scalar. It cannot be a vector. So this is the second rule. And for sequential outputs, you have to define the output as a register, because we know the sequential circuit should retain the data until the next clock appears. So it should be a register instead of a wire. And the next rule is state in sequential UDP initialized by initial statement. If the state inside the sequential, what does the sequential UDP consist? It consists of current state and next state and the output. So the current state can be initialized using initial block. Okay. And the next rule is state table can contain values of 0, 1 and x, but not z. You can have the values of 0, logic 1 and logic x only. And UDPs are defined at same level as modules. What does this mean? You cannot define UDPs inside any module, right? UDP is a separate thing because it is a user defined primitive. That module, that UDP can be used in other modules, but it should not be defined inside the module. Okay, it should sit somewhere here and then you can call the UDP inside a module, but you cannot write UDP definition inside the module. And UDPs do not support any in-out ports. It can have only inputs and output ports, but it cannot have in-out ports. So these are the rules you need to follow to define your own primitives. So what you are trying to do here is you are trying to define your own primitive that can perform whatever operation you want. So this is your output, and based on the inputs A, B, and C, based on these different combinations, you can have different outputs. If it is matching to any AND gate or NAND gate, that is, you can directly use the AND gate and NAND gate. If it is not matching to any AND gate or NAND gate, you can define your own truth table like this. So that is the purpose of the UDP. Okay, you can directly define in terms of truth table instead of solving the truth table and finding the uh, output in terms of any logic A and B and C. Instead of solving this and finding the logic, you can directly define your own functionality in terms of truth table.